Yeah, recording is rolling. It Tuesday, May 5th. Yeah, the day before the AP exam. Yeah. So you guys remember there was a update for Blue Book back on Friday. So I think you guys all downloaded that patch by yesterday. You guys got that? Yeah, definitely do that for tomorrow. All right, we're gonna pick up where we left off yesterday with a bunch of review questions. You guys are taking this exam tomorrow, 11:30 in the gym. There's a few of you guys in the media center, but we gave you guys a slip of paper the other day, had a number on it. So if you're in the media center, you know that. But most of you guys are in the gym. Your third period teacher tomorrow, let them know that you have those 11 o'clock lunch just for just for you and your classmates. And so you'll be leaving the middle of third period, because that's when 11 o'clock is. Right, and then here's the form of the page. Of course, they'll give you a blank one, so it won't have all this color coding on it. Okay. But you guys know that these are organized, roughly in the order that we cover these topics. Okay, so they look like this. Okay. All right, so here, I'm just going to jump back into the review from yesterday. Unless you guys have any specific questions, is there anything specifically you guys want to go over? All right, of course, there's a ton of stuff, so yeah, let's jump back in here. All right, so yesterday I did throw some numbers on the board, so we did solve this. So here, just a little bit of review from yesterday. All right, classic Atwood. Notes it says massless frictionless pulley. You could make this more complicated if you introduce a rotational inertia here, and you could go rotational dynamics with it. You have to consider that, well, maybe take some effort to get that pulley rotating too. But with the classic Atwood, that's just negligible, so we don't remember it. All right, so so we've got these masses and weights. Right, there's some string tension that's kind of a middle value. It's more than the small weight, but less than the big weight. All right, so we did this yesterday. There's a modified version of this, which is fairly similar, except now, you guys see that force right there? A lot of times they'll set this up. That's the only external force that matters, right? So that is the net force on the whole system. Now, there are all these other forces too, but those two blues cancel out. Those two golds are internal to the system. And this gray friction, oftentimes they say is negligible, or they get rid of it, put little wheels here, get rid of that, okay? Right, so you can still go through Newton's second law of motion. I walk you guys through a whole system approach. So I'm looking at this one weight here, this M1G, is going to be moving both masses. Okay, so there's Newton's second law as applies to the system. Okay, and then if you want to go an extra step and you say, hey, what is the tension in the string? Here's two different ways to get the tension in the string. You can focus on one or the other block. All right, so you guys see that? Okay. All right. Okay, here's the last one you guys actually saw yesterday. Do you guys remember what the end result is? A equals what? G sine theta. Yeah, it is G sine theta, right? It's just a few steps, G sine theta, right? One of the first big labs you guys did, you guys remember taking those Hot Wheels cars and rolling them down the incline? I had you changing lots of variables and you were looking at it from lots of different perspectives, right? Right. But then many weeks later, you guys learned this. And said, oh yeah, if I know Earth gravity and I know this angle, I can figure out pretty well how fast those cars were speeding up down that incline. Right, now here's a harder one. Right. Notice there's friction now. If I go back to the last slide, guys, last slide, is there any friction here? No, it's zero friction on cloud. So this could be an air hockey table used to tip up. Right? So there are only two forces, the weight and the normal force, right? And it leads to all this outcome, right? But right, this one's different. Right? What if you put a block there and started sliding down at, say, constant velocity? As soon as you see constant velocity, what do you know about the sum of all the forces?
Zero.
Zero. So therefore, what's the acceleration?
Zero.
Zero. Right? Is that true if it's moving down slowly or moving down quickly? As long as it's constant velocity, from a dynamics point of view, that's all identical, isn't it? Right? And so here I'll kickstart you guys with what you guys just told me. You guys just told me those two steps, right? Right. Now, how could you let's set up an equation along this axis here. You guys see this axis that's parallel to the surface, right? And even better if you guys are writing some stuff down here, help you out, right? What equation can you set up that falls right out of this last step?
Oh, net force is zero, plug in mg sine theta minus no.
Exactly. Yeah, mg sine theta versus what? Friction. Yeah, aren't those the two forces that are parallel to that surface, right? Which is what I'm interested in. I'm interested in those two forces have to zero out, right? Therefore, the magnitude of those forces have to be equal to each other. Right? So the friction force has to be equal to the mg sine theta. right? As long as it's sliding at constant velocity. Right? Or if it was at rest. I guess if it was at rest, that would also be true. This would just be mu s instead of mu k, but it'd be really similar, wouldn't it? All right. So I let's do this for the next step. Friction force. You guys know a very short formula for friction force. It goes what times what? Exactly. Coefficient of friction times normal force. And what is normal force in terms of the mass of the block? Yeah, mg cosine theta. So you guys see that blue substitution right there? Right? All right. So you guys are okay with every single step by step, right? Right? You guys told me the first lines, then you told me this line, and then you guys have told me every single line step by step. Okay? Okay. Ideally, you should be able to draw that diagram also. Okay? So going in for the end here, this was a lab you guys did. You could determine the coefficient of friction just by tilting up your incline to some angle until the block would slide down at constant velocity. Okay? And then you could pull up your calculator and say, oh, coefficient of friction is equal to what?
Theta.
It is tan theta. Right? You guys see this mg cancels out, right? And then it's just sine divided by cosine, which is tangent. You guys can do that? I don't know. Ooh, let's see some circular type motion. I got turntable. You guys remember turntables, turntable physics? Okay, so I give this a spin. Zoo. Right? And maybe I got 3 coins, one right at the center, and one halfway to the edge, and one right at the edge. Right? And maybe I took 5 pictures in quick succession. Right? And I'm watching them. Right, so I'm getting this picture. Right? Right. Now, there is angular motion, which is how far is this rotated? How fast is it rotating? It could be speeding up or slowing down spinning, right? Isn't that theta, omega, and alpha, right? Right. And then there are tangential values, which are like the linear type values, right? Like if you actually drove around a big circular racetrack in a car, wouldn't your odometer in your car be adding up all the miles that you drove, right? But that's like a linear type value in miles, or in our case, meters, like how many meters or centimeters, right? So I left some blanks here. So let's go through them one by one. X is equal to what? Yeah, theta r, and then V is omega r, and then A is alpha r. Right. Right. And you might have to go backwards. Guys, could you say that theta is equal to X divided by r, and omega is V divided by r, and then alpha is A over r?
I did it in the back.
No. That set of 3, for some reason they broke up a little bit, right? So 2 of them are up here. Here's the V and the A version, and then the X version is way down here for some reason. Okay, but really these 3 go together. Okay, yeah, that's the once you just stop. Okay. All right. Oh, here a little bit of trivia. 1 radian is how many degrees? It's about 57 point something, 57 point something, right? But more importantly, guys, if you are ever running calculations with angles and you are not using sine or cosine, then can you ever use degrees? No. All right, guys. If you're ever working with angles and degrees, and you're gonna see angles and degrees, you'll see 30-degree angles and probably 37-degree angles and 53-degree angles. You'll see it, right? Then it's okay to pull out sine and cosine as long as your calculator is programmed in degrees, right? But if you're just running a straight equation like this theta here has to be in radians. It has to be, if you just directly multiply an angle, it has to be in radians. Okay. Ooh. Do you guys remember centripetal force? What's the end result? What's the formula that goes right here? Yeah, mv squared over r, right? Now the version that is actually printed on your equation page is just this acceleration, which goes how? Yeah, just v squared over r, right? Because you just drop the m, you get acceleration. Is that true? Okay. That is, so we can find it real fast. It's right here. It's right here, the circular motion. They only give you the acceleration version. Now, if you say F equals mv squared over r, then they should also allow that too. Right? I don't think they'll count. Okay. But there's a Newton's second law connection between these two, because F equals ma. Right? Same. Conical pendulum. What if you have to draw a free body diagram? Go ahead and draw a free body diagram on this mass right here. What's one force on this mass? Yeah, it's weight, which is straight down. So the Earth is pulling it straight down. What's another force? The tension in the string. And guys, which force is bigger, the weight down or the tension at that angle? Yeah, the tension at that angle. How do you know the tension has to be bigger?
It has a fault.
How about this? What if I break the tension into components? Say, well, the tension is really doing two things. It's holding this weight up against Earth's gravity pull straight down, right? But also, yeah, also centripetal force, right? It's doing both those things. So there it is, broken into components. Right? Now, if you guys know there's only two proper forces on this mass, and they're both in black here: the weight down, the tension force at an angle. Right? Now, guys, could you add those two vectors tip to tail and get the net effect, the resultant? It's called the resultant. Isn't that what this green dashed vector is right here? Is
Yes.
right? If you add them tip to tail, you could go either way. Right? Uh, oh, let's break out some formulas. So, guys, if I start with this tension force and I'm playing off this angle theta, there's something to do with sine and something to do with cosine, and they represent different things. Let's go with the cosine component. What does the cosine component of the tension tell you? Yeah, mg. Yeah, yeah. Ft cosine theta is equivalent to mg. Yeah, right. Because in the vertical, that mass is not moving up or down, right? But in the horizontal, it's definitely moving in a circle, but only in the horizontal, right? So what's an equation you can set up that describes what's going on horizontally?
Sine theta.
Aha! Yeah, tension times sine theta, okay, which is the net force. And the net force, maybe I should just put this box, I should just combine this, because what is the net force? You guys know the net force. It's going to be square root of r. Yeah. Right. Right. One last detail while you guys are writing that down. I've seen AP do this before, where they give you the length of the string. Length of the string. Now, you guys know this angle theta and this angle theta, they are the same angle theta, right? If that's 31 degrees, that's 31 degrees or whatever. Right? Okay. So, guys, what if they give you the length of the string? How can you figure out this radius right here? Isn't this the radius I'm tracing out with my mouse cursor? Right? What is that radius in terms of the length of the string?
Sine theta.
L sine theta. Does everybody see that? L sine theta? Because I have a nice right triangle right here. It is L sine theta, isn't it? Ah, okay. So you might have to know that possibly tomorrow. All right, you guys get there. Get there. Uh, you guys remember if you put a ball on a string and wheel around in a vertical circle. Or how about this? How about a cup of water? Okay. Do you guys ever swing a cup of water in a vertical circle? Okay. Now there's some minimum speed to make sure that either the string doesn't go slack or at the top, or that the water doesn't fall out at the top. Right? There's some minimum speed. Right? How would you find that? Um, Actually, let's set up the diagram first, free body diagram. Let's go at the bottom. What's the free body diagram at the very bottom? What down and what up? Yeah, yeah, weight down and then a tension up. Is that true? Right. Oh, guys, why did it make the tension up so much bigger than the weight down? Okay, isn't it moving on this curved path? Moving on a curved path? So centripetal force always points which way relative to a circle? To the center of the circle. If it's at the very bottom, the center of the circle is up, isn't it? You guys see if you take the difference between those two? Right. So if this object normally weighs like 10 newtons, I bet the string tension could be like 50 newtons or something crazy, right? Maybe something like that. All right. Now let's look at the top, which is really what I want to focus on. Okay. Guys, is it the same weight at the top? Is it the same weight? Yeah, it can be the same weight. Okay. What is the tension at the top compared to the tension at the bottom?
Smaller.
Yeah, much, much smaller, right? In fact, could it approach zero, go to zero? Yeah, it could. And actually that would set up this minimum necessary speed. So let's go ahead and let this tension go to zero. Let's let it go to zero. Right. So I'm swinging it, so it's just barely getting around. Right. All right. What equation can you guys set up right here? Now the net force at the top is just equal to what?
G.
Yeah, just mg. Mg. Well, in general, it's that, but I'm getting rid of the ft top. Okay? And you guys know net force for circular type motion. I could call it mv squared over r. Okay. All right. Do you guys remember what goes in this box right here?
Root.
Yeah, root gr. Let's go. Right. And of course, here's how to get it, like the steps leading up to it. All right. So you guys can do the vertical circle. Vertical circle. Ooh, guess what's going up next? You guys ready for next slide? Orbital speed. Derive it from scratch. Go. Okay, so maybe there's a satellite in low Earth orbit, so it's just above Earth's atmosphere. It's going around the Earth. Right. But what is its tangential velocity? How fast does it have to go to stay in a pretty much a circular orbit as it's going around the Earth. Definitely do want you guys to get this one, so see if you can write this one correctly. Where'd that come from? Wait, oh, no, you did it. That was like, I think you're.
So that's the force, not an energy. Oh, you're right. Yeah, you're right. Think of the name.
Yeah. Yeah. I know. Getting there. Who got the whole thing here?
Oh man, let's see.
Yeah.
Figure that out.
Yeah. All right, that's it.
I got it.
All right.
I
So
like that with
Justin's got it. All right. Here. This is just a couple of steps, but maybe it would be helpful to have a picture. So here's a planet.
gravitation.
This planet has some mass and some radius, and I'm gonna have the satellite like just above the atmosphere, the thin atmosphere of this planet. So the satellite has a tangential velocity going to the side, okay, and that's putting it on a curved path. So it's pretty well going in a circle. Okay, guys, what's one force acting on the satellite?
Gravitational force.
Yeah, gravitational force. Is that like you could say mg? That's okay. I'm gonna write the universal form. S sub g equals g m over r squared. Is that okay? Okay. So everything in peak is referring to forces. I think that's it, right? That's the only force. That's the only force. Okay. So that force is acting as the what kind of force to keep it on a curved path? Centripetal. Do you guys know the formula for centripetal? MV squared over. Can you guys say that? Can you guys say MV squared over R is being supplied by GMM over R squared? Okay. Oh, I forgot to mark the mass of the satellite. Okay. But what do you guys know happens to the mass of the satellite in this case? Cancels anyway, right? So if the International Space Station is low on supplies, or they haul in a bunch of supplies and the mass changes wildly, right? It still needs the same orbital speed, and then change. It's the same.
Oh, yeah.
That's great. All right. So there's the setup. All right, let's see how this finishes off here. All right. So centripetal force is provided by a gravitational force. So I did that version in this case. Okay. And what'd you guys get for the answer? Exactly. Root GM on R. A good one to know.
Ready for that.
Got that.
Yes.
A good one to know. Good one to know for tomorrow. All right. Okay, let's do a little synthesis here. Do you know, in general, the gravity field of a planet, say for this guy standing on Alaska right here? G over R squared. Yeah. Now, this green one, you guys just actually, everybody should have the answer to this one. You just wrote it. Yeah, root GM on R. Right. Now, this red one, I haven't even talked about for a long time. Does anybody happen to know this one?
Root GM, 2 GM?
Yeah. Do you guys remember what process we used to derive that? It wasn't forces. It was what? Energy. It was conservation of energy.
Thank you.
I don't think AP would probably ask anything about that escape speed, right? So there is a good chance they'll ask about the orbital speed. Okay. Right. And so you guys should be able to derive orbital speed. And also good to know gravity field. Actually, didn't this one show up the other day? Wasn't this one of the last FR multiple choice questions you guys saw?
Yeah.
There was like a pendulum that was a meter long and the astronaut was swinging it. But before you could calculate the time period of the pendulum, first you had to calculate the gravity field of the planet. And they gave you the mass of the planet and the radius of the planet. Okay. I forget if I told you guys. How about that capital G? Do you either have it memorized or do you know where to find it on that formula page? It's on the back. It is on the back. Here, I'll point that out again. So normally we look at this side, but if you flip it over, there's some helpful information here too, including there's universal gravity constant. And yeah, one of the last multiple choice questions we went over, it looked like they expected you to be able to find that number and use it. So, yeah, I guess that's fair game too. Right. Uh, okay, no, the title is the spring potential energy, but I guess there's two things going on here. Right? Because there's a couple of formulas that students oftentimes confuse with springs. One is called Hooke's law, and how does that go? F equals kx. Yeah, guys, Hooke's law, does that refer to forces or energy?
Force.
Forces. We're thinking all about forces, like pushing and pulling. Right? And the more you stretch or compress the spring, the more force that takes, and the more force it pulls the other way. Blah, blah, blah. Uh, now, if I say something like, what's the work done to stretch or compress the spring, or how much energy stored in the spring, that's a different formula. How does that formula go?
X squared.
1/2 kx squared. There you go. Right, which ends up being the area of that green triangle. Yeah. So guys, that's two totally different formulas. You have one formula for force, that's Hooke's law equals kx, or sometimes you see a negative there for the restoring force. Okay. And a separate formula for the energy stored in the spring. Spring potential energy is 1/2 kx squared. Okay. You guys got the spring formulas? Okay. Guys, are you allowed to set a force quantity equal to an energy quantity?
No.
No. Okay. Now, if you have force times distance, that could be an energy because that would be some kind of work. Okay. Yeah. So you're only allowed to set like terms with the matching units to each other. Okay. Ooh, here's a real classic one. Real classic. Yeah. So Galileo drops a ball. How fast does it crash landing on the ground? I bet you guys all know the answer. Guys, what's the answer to this?
2GH.
Yeah, it is root 2GH, isn't it? Right? No, there's a whole process that leads into that. Right? That one's a good one to know the answer to. Right? But guys, if this shows up as a free response question, could you guys set up the whole thing? Say energy is conserved, potential at the top, kinetic, right before it hits the ground, equals, and then you could solve that, right? You could drive that, right? Let's do a little variation on that. Here's one's a little different. What if Galileo throws the ball? Throws the ball. Now the initial energy is a little bit different from before. What's the initial energy at the top?
1/2 m squared. 1/2 m the initial squared was it?
Yeah, yeah. Here. See, it's still got the mgh, but it also has the 1/2 m squared of throwing it. Right? And you're right, it is initial on that v because the speed is always changing. Right? Then it's about to hit the ground down here. Right? What form of energy down here?
1/2 m final squared.
Yeah, 1/2 m final squared. Right. Here, guys, go ahead. Let's take a minute. I'll derive that. Now, what's the crash speed? And you guys know it's going to be different from before because he drew it. In fact, it has to be faster than before. Okay. So what is that crash speed? All right, did you guys set up that? Did you guys set up that? All right. What variable cancels out?
Mass.
Yeah, the mass of the ball. So the mass of the ball is not the answer. All right. You guys tell me, what do you write for this very final answer?
Root 2GH plus 0.
Aha! There you go. Yeah, the square root of, and then inside the square root is the throwing speed squared plus the 2GH. Right. Yeah. Okay. Because a really common mistake that students will make is they'll say, oh, the crash speed is the throwing speed plus root 2GH, which is a different answer, and that would be the wrong answer. But you guys are looking at the right answer. Okay. You guys can derive that. All right, what's next here? Yeah, remember this? If you throw a ball straight up in the air? Right, actually, there's kind of two ways this could lead. What's the maximum height based on the throwing speed? Or if you see the maximum height, can you calculate what's the throwing speed? There's a kinematic way to do it. There's an energy way to do it. Here, I'll splash this one up here. So here's the kinematic way. Notice I picked the formula that does not talk about how much time has passed. So you can just see how high does the ball go. Here's how high it's going to go based on how fast you threw it. Or here's how fast you threw it based on how high it goes. Right. You can go either way with that. Right. And then here's the energy version, which looks very similar to that Galileo question that you guys just except it's backwards of the Galileo question, isn't it? Instead of dropping the ball from the ground, or you start at the ground, you throw the ball straight up. Right. Now, notice regardless of the method that you choose to solve this, you do end up with the same set of answers at the end. Okay. So you can go kinematic, you can go energy. All right. Ooh. This one here. All right, so a lot of parts of this one. Maybe I want to figure out what's the maximum speed of the pendulum or the speed at the bottom. Okay. Oftentimes, AP will give you a shortcut because they'll tell you the height change here. Usually they'll do that, right? But they may not. All right. What if they give you L and theta, right? Or if you take this class in college, you'll have to probably get it from L and theta anyway. So let's do some geometry. Right. Here's first thing is I want to know what this height change is, but I'm gonna look above that and I see a nice what shape is this right here?
Right triangle.
Right triangle. Guys, what is that? You guys say that brown offset distance setup? What is that equal to?
Awesome.
L cosine theta. Aha, exactly. That is L cosine theta, isn't it? Okay. Therefore, what is this actual height change equal to?
1 minus cosine theta.
Aha, there you go. So it'd be minus L cosine theta. You could factor the L out and look like that. Okay. So now you guys know how to find the height change. Great. Now that's all just geometry. That's geometry. Okay. If you want to know the maximum speed at the bottom, well, that sounds like conservation of energy would be a good choice, and it actually goes back to the Galileo type question, doesn't it? So we'll set up the conservation of energy. Okay. Now, more often than not, they'll probably release this from rest. So let's say it starts from rest here, and then you just go mgh is 1/2 mv squared, and it just turns back into the Galileo question all over again. Okay. Uh, but you might have a case where maybe like some guy's swinging on a vine and he pushes off. You guys, if he pushes off, does this gray term 1/2 mv squared also pop up? Yeah. So this may or may not be here, okay, depending on how they frame the question. And then there's your answer. Actually, this is the same as the Galileo either dropping stuff or throwing stuff, right? Except instead of h, you have this funny expression for h in terms of L and theta. But otherwise, it's the same thing, isn't it? It's the same thing. Right? You guys can solve pendulums.
Yeah.
Pendulum speed. Right? Oh, here's a real classic. Car brakes to a stop. First thing, I want you guys to set up an open system. So, yeah, we got you guys can probably come up with this free body diagram, right? Okay, weight down, normal force up, friction force resisting the motion of the car. Okay, set up an open system right here. Set up an open system. I'm talking about somebody with energy. Set up an open system. Let's see what open system you guys come up with. Walk around and see what you guys are writing in your notes here. Can you write an open system? Yeah, okay, that's a great start right there. That looks good. Looks good. Okay. Can you go to the next step? Can you substitute in the corresponding energy term? Okay. Yeah, I think that looks good. Looks good. Yeah, that was close.
Because that's an energy, that's a force. How do you make a force an energy? You have to multiply by this data. Like that. And now, is there any height change? Wait, which one is? Okay, yeah, I don't think height change. Right? It's not going up any hills. That's all. Okay. Guys, when the car comes to a stop, how much mechanical energy does it have? 0. Yeah, 0, right? 0 mechanical energy. Okay. So it starts off at the beginning with all what kind of energy? Kinetic. Yeah, kinetic. So it starts off with a bunch of kinetic energy. It ends up with 0 energy. Because it was an open system. Right? That's what fuels the filter. Yeah, it's true. Yeah. Okay, so walk around. Looks like a few of you guys. So a few of you guys put an MGH term in here. Because if you look at that picture, does that car roll up any hills? No, it doesn't roll up any hills, or it doesn't go downhill either. Guys, there's no elevation change. If there's no elevation change, are you gonna have an MGH in your equation anywhere? No. All right. So here's a really generic open system, and then here it is as it applies to the situation. So the car starts off with all 1/2 mv squared. Right, as it's braking to a stop, that's the friction force times the braking distance, d. And then it ends up with 0 mechanical energy at the end. It has no potential because it didn't roll up any hills to help it come to a stop. Right? It has no kinetic because it's not moving. Right? Really, where all the energy went is to thermal energy in the road. Do you think if you put a thermometer on the road surface, the road heats up a little bit, or the tires heat up a little bit? Yeah, right. Now, AP doesn't go into that level of detail. Right? Maybe in college, but here's all they want you to know: open system. All right. Next, let's do a substitution for this friction force. Is what is this friction force? Can you somehow bring in the mass of the car somehow? Yeah. Mu times normal force, and the normal force is equal to mg. Okay, so I can do that, right? Do that. Um, here. I'll have you guys do the algebra. Guys, solve for d. What goes in this bottom left box? So the braking distance equals what? Go ahead. Some algebra. If you can do some algebra, you can solve for the braking distance of the car in terms of what we have so far. Can you do some algebra? Solve for the braking distance. Uh, yeah. All right. So George got it. Justin got it. There. Yeah, Samantha got it. Lily got it. Ooh, yeah. Got Chloe got it. Hey, you guys all getting it over here. Yeah, Victor got it. All right, lots of winners. Great. Right, so you guys came up with that right there. Right. Here, little side thought. Notice I left it ambiguous what kind of mu it is. Is it kinetic or is it static? Because guys, what if the tires were skidding on the road and leaving tire marks? What kind of friction would that be? That'd be kinetic, wouldn't it? Because it's sliding, kinetic. But what if you have anti-lock braking system like all modern cars I think do, right? And the tires rotate a little bit so they get better traction. Then that would be what? Static. And that would help the car actually stop sooner, wouldn't it? Yeah. Right. So oftentimes I'll pull this out and say, hey, did you notice that, guys, if you triple the initial speed of the car, what happens to your braking distance? 9 times the braking distance, because 3 squared is 9. Okay. You guys know that too?
Yeah. I don't know.
Oh, you're probably gonna get asked this once. Is there's an elevator that's being pulled up, and there's some tension in the elevator cable, and they'll say, "Hey, what's the power of the motor at the top of the elevator shaft pulling up? How many watts? How many watts of power?" Okay. So, guess what is power? Power is whatever what. Yeah, work over time. Yeah. Now, work is equal to what times what? Force times distance. Okay. And where is this going? What times what? Yeah, do you see? D over T is V. Oh, so it could just be F times V, couldn't it? Could be that. Okay. No, I know one version of this that I saw show up probably about 10 years ago or so, is they also have the elevator accelerating. Guys, if the elevator is accelerating, would this V be constant or just some instantaneous value? Yeah, some instantaneous value. We should still answer the question. Okay? But what you might have to do, guys, if you know the acceleration of the elevator, is the tension now different than the weight? It is. Did we do that yesterday? Yeah, I think we did. I had you guys solve for the scale rating on inside an elevator. Okay. So you would additionally have to do that to figure out the tension in this cable. So you have to do that first. Okay. If the elevator is accelerating. Okay. Okay. And then you can get some instantaneous power value by doing this. Okay. So there could be a little more too. All right, you guys ready for next slide? Ooh, momentum. Obviously, I'm skipping a bunch of stuff. I'm trying to hit the main ones. I'm pretty sure you guys are going to see tomorrow. Every year, APS inelastic collisions. Okay. Guys, if there's any particular kind of collision you're going to see, it's going to be inelastic. Okay. Where the objects stick together. Okay. That's like AP's favorite type of collision, where they stick together. Okay. So what's the formula? Yeah, if you add up all the momentum bits before the collision, right, and then say, well, if they stick together for inelastic, they make one giant mass. So you can just add mass, right, and then times a common final velocity. You'd be like that, couldn't it? Like that. Right. Now, it looks like in my picture I have one object going to the right and one object going to the left, leading into the collision. Right. So if that's true, should one of these terms be negative compared to the other? Yeah, one of these has to be positive, one of these has to be negative to match my picture. Yeah. Right. So okay, so the momentums kind of subtract from each other, sort of, don't they? Right? Hey, could it be? Here, what if I do this? Is what if I have 2 kilograms coming in at 1 meter per second to the right, and 1 kilogram coming in at 2 meters per second to the left? So I got 1 times 2 to the right and 2 times 1 to the left. When they stick together, now what do? They just come to rest. Okay? Because guys, I have 2 times 1
Oh, correct. It's minus.
plus 1 times -2. Wouldn't that be 0? Right. So you could say there's only ever 0 momentum in the system. Say, wait, but it's moving. How is there 0? Oh, because there's positive and there's also negative momentum. So there's only ever 0 momentum in the system. And it just comes to a dead stop. Yeah. Right. You guys see that? Yeah. Ooh, impulse, change of momentum. Also, they're reintroducing the letter capital J, I think, as of like a year or so ago. So if you see capital J as a variable, not as a unit joules, that's different, but as a variable, right? I'm gonna call it delta P for change in momentum. Right? And so I give you guys two perspectives. It could be what times what, or it could be what times what. Huh?
Or and
Yeah, there you go. There's your two perspectives, right? So some mass is changing velocity. That's a impulse right there. Right? But what causes that is some force for some time. And oftentimes you'll see a graph version of this, right? Uh, I have a triangle looking graph where that can match this scenario, right? So this bat's hitting this ball, right? And if you run a slow-mo camera, or like slow-mo video footage during that collision, here's the ball striking the bat, right? And then maybe we're talking about milliseconds at a time here, right? And then the ball pushes harder against the bat, and vice versa, right? And then the ball starts to rebound the other way and finally leaves the bat. Okay? So it's really common to see graphs like that shape for this type of scenario. Okay? Guys, could the area of this green triangle represent delta P, the impulse? Yeah. Or, guys, what if this was an iceberg? Can you guys imagine this is a giant triangular iceberg? Right? And we let the iceberg melt down, but it's constrained in these aquarium walls. And so it turns into this green rectangle. Do you guys see this green rectangle? Does it have the same area on the page? Yes, it's the same area, right? Okay. And what is this average force compared to this maximum force? Yeah, it would be half, as long as you have a triangle shape, that ends up being the case. Right? So if maximum force is like 500 newtons, right, then maybe this could be 250 newtons because it'd be half that. Right? And wouldn't the average force actually feed into this equation? If you want to use the equation, you have to play out the average force, don't you? Average. So you get like the area of this rectangle, which is the area of that triangle. Right? Something like that. All right. Well, do you guys want to do a numerical example or go to the next slide?
right.
Yeah, do some numbers. All right, we'll do some numbers. Let's do it. All right. So let's say
I'll figure it out.
say I got a ball. Let's have the mass of the ball be 0.15 kilograms. Let's have it go into the left at let's say 10 meters per second. Gonna strike this bat. Pow. Okay. And the bat puts a force on it of let's say 300 newtons for a time interval of 0.1 seconds. Right. I just made up those numbers from scratch, so I have no idea what kind of crazy answer we're going to get from this. But okay. My question is then, how fast does the ball head towards the outfield? What's the final? Okay, you guys get that? All right. So like that. Okay, so yeah, these are crazy, unrealistic numbers. How many guys got 190 meters per second? Got what I got? Yeah, you did. Awesome, awesome. Okay, this was a little trick here, and it was with this negative signs right here. Bam. Okay. Remember, I told you guys the ball was thrown at 10 meters per second towards the plate, towards the bat. Okay. What I left off was, what I didn't tell you guys explicitly is that the ball is traveling to the left, but the force is to the right, and the ball ends up going to the right. That is a change in direction, isn't it? So you have to be careful with the negatives. So I say change in velocity. Isn't that final velocity minus initial velocity? Right. But initial velocity is actually a negative value, right? So, which is easy to miss. Okay? So you're actually subtracting a negative here. Okay. Okay. Now, if you count for that, then you should get that answer. All right, guys, good on impulse. Good on impulse. Yeah. So definitely look for force versus time graph. If you see a force versus time graph. Okay. All right, you guys got on impulse. I had a few posters related to this idea. I mean, here's one of these: is what if you launch a grenade and it explodes into like 2 parts, a million parts, right? And then you look at not any individual piece, but you look at the center mass of all the pieces. Does the center mass of all the pieces land exactly where the grenade would have landed if it never exploded? Right. So it'd be like that. So another okay. Another version of this is do you guys remember the Navik school bus clip where they were throwing the baseball around on the frictionless baseball field? Right. Yeah, so that's a version of this. Or you could turn this around and have this as a collision. So if 2 blocks collide. All right. So if they ask about not either individual block, but the center mass of the 2 blocks, then it's just this in reverse. Okay. All right. Let's do rotational mechanics, torque. What formulas do you guys know for torque?
R cross F.
Yeah, R cross F. And also, what about net torque? Net torque is equal to what? Yeah, I alpha. Yeah, I guess I know it too. Okay. So one common version of this is if you wrap a string around a turntable and pull the string and get the turntable spinning, and a lot of times they'll get rid of the friction with the axle so that the applied torque is the net torque. Right? But if that's not the case, if you have lots of different torques going on, you have to add and subtract them until you get the net torque first. So you guys know that? Guys, how about this angle theta? What if this angle theta is 0 degrees? Guys, if this angle theta is 0 degrees, how much torque do you get? If this is 0 degrees. Guys, if you start either like pulling or pushing.
No torque.
Yeah, no torque at all. Yeah. If you push or pull parallel to the wrench handle, yeah, there's no turning moment. Right? Ideally, you want to push it 90 degrees, don't you? So sine of 90 degrees is 1, and that would maximize your torque. Ooh, seesaw. So, guys, what if I have 3 times the mass here compared to here? So I got m and 3m. Okay. But look at their positions. You guys see I have 3x versus x? Okay. So relative to this pivot point, does all the torque cancel out? Actually, it could be relative to any point, but this is the most opportune point to start doing your analysis. But really, technically, you can pick any point and the torque would zero out. Okay? Problem with picking any point other than pivot point is you also have to consider this normal force. Hey guys, tell me, what is this normal force equal to on this diagram? Yeah, how about 4mg? Yeah, 4mg, right? Because you got mg and 3mg down, so it has to be holding up 4mg, doesn't it? So it'd be something like this. Right? A good classic question is, what if you don't know one of these weights? You could solve for the unknown weight. Or what if you do know the weights and you want to calculate where to position them? You could do that too. Ooh, scaffold. So I'm going to create this force diagram. I'm calling it a force diagram now because I'm showing you guys the locations of these forces. Right? So I got a force from the left spring scale. I got a force from the right spring scale. Tension left, tension right. Okay. This beam might have a weight. Okay, so maybe they'll throw that in the mix too. Right? And then I got another classic weight thrown on there. Okay, I got these 2 boxes. Guys, what are the 2 equilibrium conditions? What equals 0 and what else also equals 0?
Forces in equal 0, which is a 1.
Okay. Yeah, some forces. Now in this case, there's only the y direction.
Oh.
So I'm really narrowing it down. Yeah, so some of the forces in the y go to 0. And what else also goes to 0? The torque. Isn't that true?
There's your two conditions right there. Forces go to zero, torque goes to zero. Right. And what I would imagine they probably ask if you see something like this is what's the tension in one of these spring scales, right? And you might not know either one. So you have to, okay, there's some forces, there's some torques. Right? Guys, if you don't know both, like you do not know either one of these spring scale readings, I don't know what is this reading, what is this reading, right? Here's what I would do. I would pick one of these points as the pivot point, like this point right here, right? And then the torque caused by the force at that point goes to zero. So that one just leaves the equation altogether. Actually, that's exactly what I did right here. TL times zero, zero distance from the left, right? Right. And then the only unknown you would have is this tension right, and then you could quickly solve for that, right? You don't even need both these equations. You just need this bottom equation to solve for the tension on the right side, right? As long as you know everything else. Here's that classic setup of you're going to see some version of this where they wrap a string around a turntable and they start pulling the string. Okay? Is the torque equal to this R across this F? That's torque, right? Okay. Now, if they get rid of the friction with the axle, which they almost always do, then is that applied force also the net force? Or, I meant torque. The applied torque is the net torque because it's the only torque, right? Therefore, you can say it's I times alpha. You can say RF equals I alpha. You can do that. There is one more property we could analyze, which is the guys, what does L stand for in this class? Angular momentum, and that's what times what? I omega. Okay. Now, omega is angular velocity. Yes, if there's an angular acceleration, would it be speeding up spinning? So is this omega always changing? Yeah, sure is. Right. All right, well, we are about out of time, so let's close this down. Right? Yeah, we made pretty good progress.